Hello, this is Mr. Keppel. The purpose of this video series is to give my students access to my curriculum online, in case they're absent or if they just want further information and to review concepts. These presentations that I make, I call them PHYZRs, and this is PHYZR number 1, titled Welcome to Physics. I need you to please get out a piece of notebook paper which you'll be taking notes on. These notes need to be turned in. They'll be part of your classwork grade. Now what you're going to want to do is take the title. You can see the title is right here. It says PHYZR number 1, Welcome to Physics. And you're going to want to write that down at the top of your page. Now at the bottom of this slide, you can see it says Prelims, page number 1. You're also going to want to write that at the bottom of your page. So you're pretty much going to mirror what's on this slide right now. Now the prelims, that's the name of this unit. Throughout this year, there will be about 14 units. This is our first unit. It's called prelim, short for preliminaries. These are basic concepts that you need to know before you can be proficient in physics. So this is like introductory stuff. We want to get over this simple stuff before we get to the more fun and challenging material in the next units. This is page number 1. And you can see you need to make sure you label your pages, because otherwise when you go to turn in your classwork, you're not going to have your pages in the correct order. Speaking of which, you're going to place your notes in a binder. So you're going to need to buy a binder for this class. A spiral notebook will not cut it, and there's a very good reason for that. It's because you're going to be placing your PHYZR notes into this binder. Now this class isn't just taking notes every day. There are also handouts that I've made. And you're also going to be placing those handouts in the binder. Now this handout is on the metric system, and this is the handout that I'll be giving to you in a couple days. And you're going to want to put that handout in your binder. Now at the end of a unit, you're going to have about 6 or 7 pages in this binder. You're going to want to have them all in order. That's why we number the pages. And you're going to turn this into me the day of the test, and it's going to count for about 20 points. It's going to be part of your classwork grade. So again, you need to purchase a binder for this class. PHYZRs have a color code, so certain colored text has a specific meaning. So for example, if you see something written in red, it means that I think it's important. You should write it down in your notes. If something is written in yellow, it means that it's a vocabulary word. So you can write it down if you want to help improve your vocabulary. Now if you feel it's a word that you already understand and you don't really need to write it down, that's fine. It's optional, but it's very helpful. The more times you can write something down, the better you'll be, and you'll learn it better. So I highly encourage you to write that down. And the final color you'll find is green. If you see something written in green, it means that you need to discuss it with somebody. Now if you're watching these videos at home, obviously you're not going to have someone to discuss it with, but during class you'll have a partner and you can discuss it with that partner. Now, talking about physics or talking about science or talking about anything is one of the best ways to learn it. It forces you to explain yourself, to reason things out. It's very important that you discuss, and it's a very essential part of learning. What is science? Now notice, what color is this? That's right, it's green. And what does it mean if it's green? It means you have to discuss it with somebody. Now since you're watching this video on YouTube, go ahead and find someone that you can talk to about this. Pause the video, go find someone to talk to this about. Or you can just sit there and think about it. What is science? Normally when you ask people this question, they'll think of some old dudes in white lab coats. When I think of this, what is science, I think of physicists standing in front of a chalkboard scribbled on with mathematical equations and formulas, and are trying to figure out stuff. Or maybe you think of a biologist looking at plants and doing research. Or as a student, perhaps you've heard of the scientific method. This is a very common, very popular method that science teachers use to teach their students what science is. You ask a question, make a hypothesis, conduct an experiment, all that good stuff. You've probably heard of that before. Now this is our first slide. It says number 1, what is science? So let's look at our notebook paper, and you're going to want to write this down in your notebook paper. This is the first section of the PHYZR. So take a moment and write that down. Number 1, what is science? Now the word science comes from the Latin word scientia, which means knowledge. Notice this is red, which means we need to write it down in our notes. So go ahead and write that down on your notes. The word science comes from the Latin word scientia, which means knowledge. So you notice that science comes from the word knowledge. Now if we were Latin, science and knowledge would be the same thing, because the Latin word scientia, or science, literally means knowledge. If you look up the word science in a dictionary, this is what you'll find. Whoa. It's a very complicated, long-winded sentence, but here we go. Let's try to break this down. Science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. Now let's try to break this down. So first I see the word systematic. There's a system, there's a method of science. Science builds knowledge. It organizes that knowledge. And the knowledge that we gain through science has to be testable. And science makes predictions about the universe. So if we were to summarize this up, we can say that science is knowledge that has been confirmed by an experiment, which means that we're pretty sure that scientific knowledge is correct as far as we know, that every experiment that has been performed reinforces our understanding and our knowledge. Now notice this is yellow, this text down here at the bottom, which means it's a vocabulary building, and the vocabulary here is science. So go ahead and write that down if you want to help understand and further your vocabulary knowledge about the word science. Number 2, scientific theory. So here's what we have written down from the last part, what is science? So let's go up a little bit here, and we're going to add a second heading to this. Number 2, scientific theory. What is a scientific theory? Again, I'll pause and give you a moment to think about this or to discuss this with someone sitting next to you. Scientific theory is really difficult for a lot of people to understand. They think that a theory is just a guess or something that's not true. But in fact, it's the furthest from the truth. Let me give you guys a little way to think about it. So this is the way science works. So you come up with an idea. That idea could be anything. Any idea that you have about the universe. And what you want to do is perform an experiment to test that idea. You got to test it out. That's what makes it science. And then you have to ask yourself the question, after you perform this experiment, does the evidence that was gathered in the experiment, does it support my original idea? And if it doesn't, so if the answer is no, that your evidence does not support your idea, then we have to conclude the idea was wrong. Inevitably, what we do then is we try again, come up with another idea, perform another experiment. Eventually, you're going to have an idea that agrees with the experiments, where the evidence supports the idea. And when this happens, when you come up with an idea and the evidence from experiments confirms the idea, that's called a theory, a scientific theory. But science doesn't stop there, because how do we know that we've performed every possible experiment? You can never perform every possible experiment. And so we continue to test our theories, perform additional experiments. We repeat this process over and over and over again, inching closer and closer to the truth with every additional experiment. A scientific theory is an explanation of the universe that agrees with all known evidence. So a theory is not just a guess. In fact, a scientific theory is the highest form of scientific knowledge. A theory has been repeatedly confirmed by experimental evidence. So a scientific theory is an explanation that agrees with all known evidence. You need to take this word seriously. A theory is not just an idea. It's an idea that has been confirmed by an experiment. Maybe you guys have heard this song. It's by They Might Be Giants. I'll put a link for it in the video description. But it's called Science is Real. I was listening to that song a lot over the summer. I want to give you guys an example of a scientific theory. We're going to do a very easy theory based on this question. What shape is the Earth? I'll pause for a moment for you to discuss this with someone or with yourself. I told you we're going to start off with an easy theory. Now, as you can see from this picture, when we look out at the Earth and we make very simple, basic observations of the Earth, we can see that based on simple observation, the shape of the Earth is flat. Simple observation. We're just looking at the Earth. We're standing on the surface of Earth. And we're looking out. It looks flat. We can call this the flat Earth theory. We came up with an idea. The Earth is flat. We performed an experiment. We looked out at the Earth, and it looked to be flat. Now remember, a theory can never be proven. It can only be disproven. Just because the experiment says that the experiment didn't disagree with your idea, that doesn't mean that your idea is correct, because how do you know that you didn't perform the one experiment that could disprove your idea? So a theory can never be proven. You can only disprove the theory. That's why we have to continue to test our theories. We have to come up with additional experiments. And we perform those experiments over and over and over again. And here's why theories are so powerful. Because even if one piece of evidence cannot be explained by a theory, then the theory is wrong and it must be changed or discarded. No matter how much you like that theory, if you find a piece of evidence from an experiment that says your theory is wrong, you have to throw out your theory. So let's go back to our flat Earth theory. At this moment, we only have one piece of evidence, a simple observation of the Earth. We need to perform additional experiments. Let's make additional observations. Let's gather more evidence and see if additional pieces of evidence can support the theory. If we find a piece of evidence that cannot be supported by the flat Earth theory, then we have to throw that theory out. So here's a question. Is flat Earth theory real? I will give you a moment to discuss this question. I have a story to tell you. The story takes place 2,000 years ago in ancient Egypt. Here's a satellite photo of Egypt. This story is about this guy. His name was Eratosthenes. And Eratosthenes noticed something very interesting. At a certain time during the year, in the city in Egypt called Syene, people noticed that the sun was directly overhead. And in fact, you can look down a well, straight down a well, as you can see here, and the sun would shine at the bottom of the well, which indicates that the sun is directly above the well. You can also notice in this picture that none of the objects are casting shadows, or you could rather say that the shadows are cast straight beneath the object. So Eratosthenes noticed that in this certain day of the year that there are no shadows cast in this town of Syene. Now, why is this interesting? Well, it's interesting because back in Alexandria, where Eratosthenes lived, on that same day of the year, objects cast a shadow. So Eratosthenes realized something that completely changed our understanding of the planet that we live on. His observation was that shadows are not the same everywhere on Earth. In certain places, the same time of day, you have a shadow, and in other places, there are no shadows. That shadows depend upon where you are on the planet. Now, what does this have to do with flat Earth theory? If the Earth were flat, then when the sun shines down on the Earth, there's no possible way that you could have two different shadows on two different parts of the Earth. And you can see here that this line just doesn't match up. The sunlight comes straight down if the Earth is flat. This just doesn't add up. This just can't be right. So that means we need a new theory. The flat Earth theory is wrong. Flat Earth theory cannot explain the shadows. It just can't. If the Earth were flat, then all the sunlight would come straight down, and there's no possible way that shadows can be different at different parts of the Earth. It just doesn't add up. But here's the thing. A round Earth or a spherical Earth theory can explain the difference in shadows. So notice now that because the Earth is curved, the two places are not equal to each other. In fact, the sunlight is still shining straight down, but now you can see that the column is actually tilted because it's on a surface of a curved planet. And it's that curvature of the planet that causes the shadows to be different at these two locations. So the flat Earth theory cannot explain the shadows, but a spherical Earth theory can. We are forced to conclude that the Earth is round. The Earth is not flat. This experiment of looking at the shadows has disproven the flat Earth theory. And now we must accept a spherical Earth theory. So here's a question you might be thinking at this moment. If the Earth is round or spherical, then why does it look flat? When we look out at the Earth, why does it look flat if it's actually round? I'll give you a moment to think about that, to discuss it with somebody. Here's a really awesome video. This video was taken by, I believe, is the Messenger spacecraft. And the Messenger spacecraft was doing a flyby of the Earth on its way to Mercury, where it's currently orbiting Mercury right now, performing its scientific mission. Now, when the Messenger spacecraft flew past the Earth, they actually took a series of photographs over the course of about 25 hours. And this video stitches those photographs together into a time-lapse video. Now realize that in our digital age of sending spacecraft into space, we have tremendously more observational power than Eratosthenes had 2,000 years ago in ancient Egypt when he just looked at the shadows on the ground. We actually have photographs of the planet that we live on. We can very clearly see in this photograph that the Earth is round, that it's a spherical shape. Now, what's really fascinating, though, is it's not actually a perfect sphere. If I draw a sphere on this Earth, on the planet here, this is a perfect sphere. I drew this in PowerPoint. This is a perfect computer-generated circle. And what you notice here, the Earth is not a perfect sphere. You can see there's a little part right here that bulges out a little bit, and this is the part along the equator. Now what you have to realize is that the Earth is spinning, and as it spins around the equator, that part actually bulges out a little bit. So the Earth is not a perfect sphere. In fact, we now know today that the Earth is an oblate spheroid. An oblate spheroid. Now, the way to think about an oblate spheroid, the shape, is it's sort of a lopsided circle. And there's an object that everybody knows that's an oblate spheroid. That's right, it's a football. So notice how the football has sort of this circular shape here, but then it bulges out along the equator. Well, the Earth is shaped similar to a football. Not as drastic as a football. Obviously, the football is very oblate, whereas the Earth is just a tiny bit oblate. So let's review our theories. We started with the flat Earth theory. The flat Earth theory was proven wrong by Eratosthenes' observations of shadows, which led to the development of a spheroid Earth theory, which was then proven wrong by detailed satellite observation, and now we're left with an oblate spheroid Earth theory. Now this is what's really interesting about theories. See, a lot of people are like, oh, it's just a theory. Oh, but see, theories, we're not suddenly going to go backwards. Like, we're not going to wake up tomorrow and go, oh, we were wrong. The Earth is actually flat. Because we've disproven the flat Earth theory. So the flat Earth theory is completely rejected. We completely reject that theory. Does that mean that the oblate spheroid theory is the true theory? Is the 100% truth of the shape of the Earth? It doesn't. But we know that the oblate spheroid theory is the best theory. It fits the evidence the best. In the future, we may find that the Earth isn't an oblate spheroid, but when you compare these three theories with each other, you can see that as we progress from the flat Earth theory to the spheroid Earth theory to the oblate spheroid, the differences between each theory grow smaller and smaller. So you can think of science as this gradual process of inching ever and ever and ever closer to the truth. Now, technically, we will never arrive at the truth, but our theories are the best that we can get, the closest that we can get. And this is what science is all about. Scientific theories are our highest form of scientific knowledge, that no experiment has been performed which has proven that theory wrong yet. But remember, it only takes one piece of evidence to prove a theory wrong. You can never prove a theory correct. So the oblate spheroid Earth theory represents our best understanding of the shape of the Earth. It is not the true understanding, but rather it is our best understanding. Here's another question. What is physics? Obviously, this is a physics class. I want you to think about what is physics or discuss what is physics. Here are a few of the images that come to mind when I think about physics. The word physics comes from the Latin word physis, which means nature. This is a new section. This is section 4. What is physics? So make sure that you copy this red text down under the heading 4. What is physics? Now, a lot of students are confused when they hear that physis means nature because they think nature, wasn't that biology, like plants and the environment? And actually, it's not what nature means. So nature is actually a way of referring to the universe. So perhaps it would have been, in English, the word universe is probably more closer to what we mean by nature, since nature sort of has this, in modern times, this tendency of invoking the environment for people to think about, nature. That's what you think of. You think of trees and animals. But when I use the word nature here, I'm actually referring to the universe, to everything in the universe. If you look up the word physics in a dictionary, this is what you get. It says physics is a natural science that involves the study of matter and its motion through space and time. So again, let's break down this definition. It's a natural science. This means that it's not a social science. It's a natural science. And we study matter. We study its motion through space and time. And this is why I love physics, because if you think about it, what has matter? What moves through space and time? The answer is everything. Physics is the study of the natural world, which means in physics we study everything, from atoms to bows and arrows to computers, everything. Physics is the ultimate science. We study everything in physics. We don't limit ourselves to any one particular field. We study everything in physics. It's the study of the entire natural world. Now, the goal of physics is to create mathematical models that explain how the world works. Mathematics and physics go hand in hand. In fact, you could say that mathematics is the language of physics. In fact, math just gives us a way of thinking about physics. It's just a different tool set, and it's something that you'll get familiar with and comfortable with the more that you study physics. In fact, when I was a student and I was learning about math and physics, I really didn't like math. I started out not enjoying math at all. But once I started to take physics and I really could see the connections between math and reality, I started to really enjoy math so much more, because math just has meaning behind it. And if you don't take physics, if you don't apply the math, you can never appreciate that deeper, amazing meaning behind math. I'll give you guys an example of a mathematical model. So let's take, for instance, a car. So here you see a car traveling at 25 miles per hour, and that was the stopping distance. If we look at it traveling at 35 miles per hour, and finally traveling at 40 miles per hour. Now imagine that we perform this experiment. We can actually make a graph. On our vertical axis, we can graph the stopping distance. And on our horizontal axis, we'll graph the speed. So you can see in this graph, when the car was traveling at 0 miles per hour, it stopped in a distance of 0 meters. When the car traveled at 20 miles per hour, it took, what was that, about 17 meters? And as the speed gets progressively larger and larger and larger, the distance it takes to stop also increases, but it's increasing in this upwards curve. The slope is getting steeper. It's not just a straight line, it's actually sloping upwards, curving upwards. So our mathematical model will have to include that. Now, obviously, this is a little bit beyond our scope in the first lesson of a physics class, but there's an equation that can actually describe this. There's a mathematical model, and I'll show it to you. This is a simplified model. We're making a lot of assumptions here, but we can say that the distance that it takes for a car to stop, that's d, is equal to the speed squared divided by 2 mu g. Now g is the gravitational constant of acceleration, and mu is a coefficient of friction. You don't have to worry too much about that, but the idea here, all I want you to understand here, is that physics uses mathematical models to explain how the world works. And so you can see in this equation that the distance it takes for your car to stop depends on how fast you're traveling. And we see it depends on it as a square. And that's the reason why this graph slopes upward like a parabola. You can see it very clearly here in this mathematical relationship. So that's what physics is all about. It's about creating these mathematical models to explain how the world works. Here are just a few formulas that we'll be seeing in this class. These are basic physics equations. You can see one for average speed, there's Newton's second law, and all these various equations that we'll be studying this year. I just thought it'd be fun to show these on our first day. If this is scary to you, don't worry. We're going to break it down into very small pieces as we move forward. I'm sure this is a little bit overwhelming if this is your first physics class. Now, eventually you'll get really good at physics if you continue to study it. And notice that I said these are basic physics equations. Let me show you some non-basic physics equations. These equations are Maxwell's equations of light. And these equations basically describe light. Well, actually describe electromagnetic waves. And you can see a lot of symbols in here that are confusing and crazy. But to a physicist, there's actually a very deep beauty behind this. That this is explaining light. It's explaining electromagnetic waves. I want to end our lesson today by showing how physics fits together with all the other branches of science. So as you know, there are 3 branches of science. There's biology, there's chemistry, and there's physics. Now, biology is the study of plants and animals. Chemistry is the study of chemicals and matter. And physics is the study of the physical world of everything. Now, how do these sciences fit together? Well, basically, every science can be explained in terms of physics. I mean, if you notice here, there's a hierarchy. That physics is everything. Chemistry is the chemicals and the matter within the physical world. And biology is the plants and animals made of the chemicals and matter that are within the physical world. So you see that every science can be explained in terms of physics. Let me break this down a little bit more into detail. Here's an example. Let's think about cells, about living things. So all living things, everything. That's you, bees, dolphins, birds, everything. All living things are made of cells. Now, what branch of science would study cells? Biology is the study of living things. So this would be biology. If we want to study living things, we're gonna use biology. But we know that all living things are made of cells, and cells are made of chemicals. Here's a picture of DNA. DNA is made of chemicals. You can see these circles here, these little circles, these circular structures. Those are all atoms. And those atoms are bonded together to create the structure. Now, chemicals is chemistry. So you see that to understand biology, to understand cells, if cells are made of chemicals, you have to understand chemistry. But we can go deeper. Chemicals, these molecular bonds, are held together by electrical forces. And electrical forces are the domain of physics. So you see, we started with all living things. And we've broken it down to its fundamental pieces. And at those fundamental pieces of those atoms held together by these invisible electrical forces, that is physics. So everything, every science can be explained in terms of physics. That doesn't mean that you have to know physics in order to be a biologist. It just means that biology is a subset of physics. Here's another way to think about it. If we draw a Venn diagram of science, and this circle represents all of science, this circle would be physics. And within this circle, there'd be a smaller section for chemistry. And within the chemistry circle, there'd be a smaller section for biology. Another way of thinking about it is that chemistry is a smaller part of physics, and biology is a smaller part of chemistry. That all of these sciences can be explained in terms of physics. I like to say that physics is the mother science, that physics was the first science, and these other sciences have branched off from physics. We would have never been able to understand DNA if we didn't understand electrical forces. We would never be able to understand biology if we didn't understand DNA. DNA is the central idea behind biology. So every science is related to physics in some way. That's why it's so important to understand and to study physics, because physics can explain everything. It's not just limited to living things or to chemicals. Physics is the study of the entire natural world. To end today's lesson, I have several questions to check your understanding. First question is, where does the word science come from? This is a vocabulary question. That's why it's in yellow. So write this question down on your notebook paper, on your notes, and answer it. The next question is question B. What is the goal of physics? What do physicists try to do? Next question. Do you think physics is important? And explain your reasoning. If you think it's not important, tell me why you don't think it's important. Or if you think it is important, tell me why you think it's important. And lastly, this is a green discussion question, which means discuss it with someone and then write your answer down. I want you to come up with a question that could be answered by using physics. Be creative here. Don't be afraid of coming up with some silly questions. Because remember, physics can answer anything. Physics is the study of everything. So please answer these questions. Make sure that you've written down your answers in your notes. And that's it for today. Have a wonderful day. This has been Mr. Keppel. I'll see you in class.